Hello students, in this video we'll see an example of finding the long-time equilibrium state of a two-state Markov chain. Let's be given a two-state Markov chain. The two-state Markov chain has with matrix P, which is going to be a 0.6, 0.4, 0.2, and 0.8, right? And I like to think of these as saying like maybe this is like the wins, and this is the losses, and then win, then the loss. So in this sort of interpretation, there's many other interpretations of this, but you can say the probability of going from a win to a win is 0.6, the probability of going from a win to a loss is 0.4, from a loss to a win is 0.2, and from a loss to loss is 0.8, for example, right? And of course, let's write this in more simple terms, right? So let's write these in terms of fifths. So this is going to be 3/5 over here, then it's going to be 2/5 over here. That's going to be 1/5 over here and 4/5 over here. If you don't like decimals, you can do fractions instead. Okay, so now I'd like to find the long time behavior of this thing. So what do we know? We know that if alpha n is the distribution probability that xn equals let's say this is like a 0 or a 1 equals 0, probability that xn equals 1. Okay, is given by alpha 0, the initial probability configuration, and then the matrix P to the power n, right? So here we have the probability, so probability, the matrix P over here, P to the power n. Okay, so I'd like to find the matrix P to the power n, and then I'd like to figure out what the long-term distribution of this is going to look like. So let's do it. So of course we need to find the eigenvalues to find P to the power n. Of course, all the entries in this matrix are non-negative, so this is an ergodic matrix. So Pij is greater than 0, so our matrix is called ergodic. Okay, and ergodic matrices have nice stationary distributions. Okay, and so let's find the eigenvalue. So what's the eigenvalue equation? The eigenvalue equation is going to be determinant of 3/5 minus lambda, and then 2/5. I subtract off lambda from the main diagonal, 1/5, and then 4/5 with minus lambda equals 0. So this is 3/5 minus lambda, and then 4/5 minus lambda over there. And then a minus 2/25 equals 0. I'm going to multiply everything by 25 to make my life a little bit easier. If I multiply by 25, this is going to turn into what? A 3 minus 5 lambda, and then a 4 minus 5 lambda, minus 2 is equal to 0. So over here, what are we going to have? We're going to have a 25 lambda squared, and let's see, a negative 20 lambda, and then a negative 15, so that's negative what? Then we have a negative 20, and then a negative 20, and then a negative 15, so that's negative 35 lambda. And then I have a 12 minus 2, that's a plus 10 is equal to 0. I'm going to divide by 5, so I have a lambda squared times 5, and then minus 7 lambda, and then plus 2 is equal to 0. So if I factor this, I have a 5 lambda, and then a lambda. And I think I need a negative 1 over here, and a negative 2 over here equals 0. So my eigenvalues are lambda equals 1, and lambda equals 2/5. 2/5 is going to be nice, because now what I can say is what are my eigenvectors that correspond to this? Well, clearly the eigenvector that corresponds to 1, 1 is going to be this will have an eigenvector of 1, 1. So if I subtract off 1, 1, 1 is going to work. So this eigenvector over here is going to be 1, 1. And what's the eigenvector for 2/5? Let's compute it over here. So if I do the 2/5 calculation, if I subtract off 2/5 from the main diagonal, I'm going to have a 1/5 2/5. That's going to be a 1/5 2/5. And then if I subtract off 1/5, I'm going to get a what? I'm going to get a 1, and then a 2/5, 1/5, 2/5. That's my matrix over here that corresponds to this matrix over here when lambda is equal to 2/5. So it's clear I can choose this to be my eigenvector over here. So I can do a negative 2, 1 is the eigenvector that corresponds to 2/5. So now let's form our diagonalization. So what does our matrix look like? Our matrix now is the following form. Our matrix P is really this diagonal matrix, is really the eigenvector matrix. I'm going to do a 1, 1, then a negative 2 and a 1. Then I have a 1 up top over here, because that's my first eigenvalue, a 0, 0, 2/5. And I have to do the inverse of this matrix over here. The inverse of a 2 by 2 matrix is I flip the diagonal entries, so nothing happens. I negate the off-diagonal entries, and I divide by the determinant of this matrix. The determinant of this matrix is 3, so everything over here gets a 1/3, 1/3, 1/3, 1/3, and that's the inverse of this matrix, okay? So what am I using? I'm using the fact here that if I have A, B, C, D, inverse, this is going to turn into, the inverse of this is 1 over A, D minus B, C. That's 1 over the determinant of the matrix. If it's invertible, that makes sense. I flip the diagonal entries D to A, and I negate the off-diagonal entries B and C. And we can easily check that that's going to be, if I do the first entry, I'm going to have AD minus BC, that's going to cancel. Then I'm going to have an AB negative, AB positive, so we can see it works. Okay, excellent. And so now, therefore, what's P to the power N? So now, for the reason we do this is because now for diagonal matrices, for these diagonalizable matrices, the nth power of the matrix is just the nth power of the matrix inside over there. So now, as I let N go to infinity, as N tends to infinity, what's the steady state looking like? Well, we're going to have a 1, negative 2, 1, 1, and then a 1, 0, 0. Now, 2/5 to the power n as n goes to infinity goes to 0, okay? Then I have a 1/3, then I have a 2/3, then I have a negative 1/3, then I have a 1/3. Great. And so if we do this calculation, this becomes a 1, negative 2, 1, 1. And then I'm going to have a 1/3, a 2/3, and then a 0 and a 0, a 1/3, and a 2/3, and a 0 and a 0. And if we do this, what we get, we're going to get the matrix that looks like a, let's see, I'm going to get a 1/3 over here, then a 2/3 over here. Then we're going to get a what? We're going to get a 1/3 over here, and a 2/3 over here. Beautiful? Okay. And we notice that the columns are constant, right? The columns over here are constant. That's excellent. It's now in particular, let's look at this. What do we know about this vector 1/3, 2/3? Well, if I take 1/3, 2/3, 1/3, 2/3, and hit it on the right with 3/5, 2/5, 1/5, and then 4/5, what's going to happen over here? I'm going to have the first entry over here is going to be 1/3 of 3/5. So let's write it very carefully over here. So we're going to have 1/3 of 3/5. That's going to be a vector. 1/3 of 3/5 plus 2/3 of 1/5. And then the second entry in this is going to be 1/3 of 2/5, 1/3 of 2/5, and then 2/3 of 4/5. Okay, that's the vector we're going to get if we hit this, multiply this initial configuration by the transition matrix. And so this is what? This is going to be 3 over 15 plus 2 over 15. That's 5 over 15. 5 over 15 is 1/3. And then if I do the next one again, if I do 2 over 15 plus 8 over 15, that's 10 over 15, that's 2/3. So in other words, what's happening over here? So in other words, we've just shown that if this configuration, if we start over here with alpha 0, if alpha 0 is the vector 1/3 probability of a win, 2/3 of a loss. After I do one step, I'll get alpha 1, and alpha 1 is also going to be 1/3, 2/3. And therefore, if I do one step into this pattern persists, I have found now that this is going to be an equilibrium distribution. So this is my initial equilibrium or steady state for this Markov chain, okay? And the fact that the matrix was ergodic, I knew that since I had an ergodic matrix, this was going to have to exist. Thank you very much.